Good afternoon, and welcome to the 2022 Arnold Ross Lecture, sponsored by the American Mathematical Society. My name is Tom Barr. I'm the AMS Programs Director, and I'm here to offer some greetings, thanks, and a bit of information before we introduce today's speaker. I want to take a moment of personal privilege here. It's a rich moment for me to be here on the BU campus in the presence of the PROMYS program participants. It turns out I was on the BU campus when the Dynamical Systems Institutes were running back in, dare I say, the 80s. And I was here on the occasion of the first year of the PROMYS program. So I remember a number of those participants joining us for some of the presentations in the Institute. So it brings back fond recollections for me to be here and to introduce the speaker. I'm pleased to report that AMS, through its Epsilon Fund for Young Scholars, provides financial support for the PROMYS program, as well as for other high school math camps around the country. And indeed, today we have some math camp folks joining us via Zoom. They are coming to us from the Ross math camps at Rose-Hulman Institute and at Ohio Dominican University. So we will be hearing in just a moment from Jim Fowler, who will be introducing our speaker, and he is on site with those participants. One word about the AMS. The AMS was founded in 1888. It's an old organization, and it's headquartered just down the road in Providence, Rhode Island, about 1 hour from here. It furthers the interest of mathematics research and scholarship. It serves the national and international community through its publications, its meetings, advocacy, and programs. AMS in particular supports mathematics education at all levels and fosters awareness and appreciation for mathematics and its relevance to everyday life and much more. A little bit about the Arnold Ross, that program. Around 1957, Arnold Ross started a program at the University of Notre Dame for talented pre-college math students. As a professor and chairperson in mathematics at Notre Dame, and later at The Ohio State University, he was involved with this program until the year 2000. In the 1990s, with the help and support of Professor Paul Sally at the University of Chicago, EMS established the Arnold Ross Lecture Series, which is dedicated to the allied purpose of fostering connections between young mathematicians, that would be you, around the country, and leading researchers and their work. So I'll wrap up my remarks by giving a few moments of thanks, a few words of thanks to those who've helped to make today's event possible. Li Mei Lim of the BU Math Department here has been very helpful in getting things organized here. Jim Fowler, chair of the Arnold Ross Lecture Committee. Kim Kuda and Eileen Muehlbauer, who are our AMS staff members who have worked tirelessly to make this happen. So now I will turn things over to Jim Fowler, who will, via Zoom, introduce today's speaker.
Hopefully you can hear me okay. I'm going to take that as a yes. So yeah, I'm Jim Fowler, and I'm here in Columbus, Ohio, and yeah, I'm chair of the Arnold Ross Lecture Series Committee. Today's speaker is Noam Elkies, professor of mathematics at Harvard University. And I think a lot of us know Elkies from just beautiful work in mathematics, stunning examples of elliptic curves. But speaking personally, I mean, I also know Professor Elkies as an educator. A couple decades ago, I took courses from Professor Elkies. And what really strikes me, thinking back to 20 years ago, was just how beautifully constructed the problem sets were that he crafted. These problem sets where you discovered for yourself what a cocycle was. And I think those problem sets, just by virtue of being so well constructed, really led to just a wonderful mathematical community. A community that Noam was directly supporting. He was visiting with us in the dining hall, sometimes giving us hints to get us unstuck. and just sharing with us his enthusiasm for mathematics and for music and for life. And that was certainly a transformative experience for me. So when I think about this lecture series and Arnold Ross and Paul Sally and summer math programs, I think a lot about just great problem sets that engender, sort of fantastic mathematical communities. So I think it's quite appropriate, and we're truly honored to have Professor Elkies speaking in this lecture series today. Today's talk is titled Spherical Packings and Codes in Various Dimensions. Certainly super timely, given Vyazovska's field medal in sphere packing. So now we'll zoom back to Boston to hear from Professor Elkies.
Thank you very much. Am I on?
You are.
Okay, well, thank you very much for the introduction and for the invitation to give this talk, which actually came 2 years ago, but well, more about that anon. I'm glad to finally be able to give the talk here and to be in person, and also to have some of an audience remotely, which I guess became possible in part in the past 2 years. Is my title sheet still on?
Yeah.
Yeah. Okay. So the topic I chose is spherical packing. So illustrated here by a packing of equal spheres, which in 2 dimensions look like circles, which turns out to be the densest way of packing equal circles in equal circles or equal spheres in 2 dimensions. And this figure here, which you find out, no, it's in a, yeah, type okay, but is it okay? Am I still on? Anybody? Not here. Okay, I can see the chat from here. Am I?
I still see you as on.
Okay. Well, I'm certainly on for however many people are here. So as I was saying, spherical codes I'm introducing here by this diagram, which shows 6 vectors, and it's up to you whether you want to think about them as 6 unit vectors in 2 dimensions, which form the best spherical code for 60-degree angles in that dimension, or you can think about them as vectors in 3 dimensions, which we will see are the best way of, in fact, the unique way of putting 6 points on the surface of the sphere so that no 2 of the vectors are closer to each other than spanning a 90-degree angle. So a bit of an overview. I will introduce the question of sphere packing, beginning with dimension 2 and then going on to 3 and higher, and report briefly on what's known about it. Go on to what will occupy by a small fraction the majority of our time, which is the somewhat more tractable but still still challenging and a significant problem of spherical codes, which we will, among other things, think of as sphere packings on the surface of a fixed sphere. We will, in particular, show that the simplex code and the hyperoctahedral code, which is a fancy way of just saying, like imagine in 3 dimensions, well, you have seen a picture of a methane molecule. So you have a carbon center, then you have a hydrogen atom going this way, one going this way, one this way, one this way, forming a regular tetrahedron. That turns out to be the best you can do there, perhaps not surprising. And the hyperoctahedron is just the n-dimensional version of the regular octahedron, whose vertices are the 6 vectors in 3 dimensions that I sketched earlier. And finally, come back to sphere packings and see that one of the uses of spherical codes is to get an exponential upper bound on the sphere packing in Rn. For anybody here who heard the Arnold Ross program given by Henry Cohn in 2014. I apologize that there be some overlap, but I trust that not many people here were at this talk in 2014. There have been a few things that happened since 2014. One of them was mentioned by Jim Fowler in his introduction, and the other of which is the reason that I'm here today as opposed to in the summer of 2020. And so this is a picture that was taken in Domino Park in Brooklyn, New York, just across the river from where I used to live for, let's say, too many years. And it shows an early accommodation. Back then, we didn't know much, and nobody was vaccinated yet because the vaccine was still some months in the future. And so they laid out circles on the park and said, okay, I mean, you can go out in the park, but to make sure that we don't have people potentially infecting each other, each person or group who's already like a pod has to stay within their own circle. And this was popping up not only in New York City, but also across the country. So here is a similar and larger such picture from, maybe it's easier to see this way, from Dolores Park out on the other coast in San Francisco. And so this is posted in various, shown various newspapers and social media. And of course, there is a bunch of math people who are saying, what the heck are you doing? If you want to accommodate as many people on this huge tract of land in Dolores Park, don't set up the circles like this in like this in a square lattice, but do it in a triangular lattice. Now, what do I mean by that? And why is that better? And what does it have to do with sphere packing? I mean, so what's happening here is each one of these circles, well, it's a circle, so it has some fixed radius, which is however much they're allotting to a person or a group in the park. And the circles are far apart from each other, which can be measured in various ways. Presumably, the idea was that any two of these circles are far enough apart that even if you have one person at the extreme of their allotted circle and another at the extreme of their allotted circle, they are at least at some distance, let's say d from each other. And that means that if the radius of the circle is r, then any two of these circles are a distance at least 2r, the diameter of each circle, plus the distance between them. But you can visualize this in various ways. This problem is the same regardless of however you allot this distance between 2r and d. You can shrink any of the circles to 0, and then any two of them are distance 2r plus d, or you can bring them as close as possible together. You're not going to allow anybody to actually be at the boundary of these expanded circles, but then the condition that the small circles should be a distance d from each other is the condition that the large circles should not overlap. So basically, an equivalent problem, well, there are various ways of stating it. One of them was, pack points densely, centers of circles densely in some region in the plane, so that no two of them are closer than some distance, some fixed distance apart, or equivalently pack unit circles. Well, it's up to you what to call the unit. So let's call the unit the radius of one of, half the distance, the diameter of one of these big circles, so that no two of these circles overlap. Fortunately, I can go to my local bank and buy lots of identical circles at the price of, well, $4 to $1. I could have bought cheaper ones, but it would be harder to see the picture. So I didn't buy enough to cover this entire picture, but I covered enough to show the idea that many people were thinking about, which is what you should do is you should take each row of these quarters and shift it over a bit so that it's above, the hole between two adjacent circles at the bottom layer, and then slide it a bit down. And then do the same thing with the next layer and slide it a bit further down and keep going in this way. And when you do that, instead of this picture, you get this one, where the circles are the same size, but if you compare the two pictures, here there are 11 of layers. Here there are almost 13. I mean, if you do the geometry or trigonometry, however you like to think about it, each one of these distances is still 2, but by Pythagoras, this distance is the square root of 3. Square root of 3 is, of course, less than 2, and it's less than 2 by about 13. Excuse me, it's a 13 to 15 ratio, to a very good approximation. Those of you who are at this program learning about Pell's equations and the like can learn some wonderful stuff about what do the best approximations look like and what this has to do with the algebraic number theory of quadratic fields. But we don't need to go that far here. All we have to do is to observe that you could have packed, whatever it is, 14, 15% more circles by doing this. And of course, this is not something that you need to be a mathematician to see. Nature has been doing this even before bees rediscovered it. This is a picture of what's called Brechat HaMeshushim, which is Hebrew for the pool of hexagons. It's called hexagon pool in English, but that might make you think it's a pool that looks like France. No, it's a pool which is surrounded by these basalt columns, which in cooling down and shrink, and they've eventually separated into these columns, and they're more or less in this hexagonal arrangement. Where are the hexagons? I mean, hexagons are what happens if you imagine maybe taking these circles and squishing them so that each one of them, or conversely blowing each one of them up, so each one is surrounded by a hexagon. And that's basically the picture you get here. The picture you see in a honeycomb, and so forth. So, of course, that's a solution in 2 dimensions. I haven't proven to you it's the solution in 2 dimensions, but it does turn out to be the densest way of packing circles of equal size in a large region of the plane. And you can ask the same question, not just in 2 dimensions. You can ask the question, well, going down in 1 dimension. Well, okay, first of all, I should explain, sphere is a very old word, and mathematical notation for balls and spheres has come more recently, to the point that this whole topic was known as sphere packing before mathematicians converged on the terminology that the set of points at distance at most r from the center is a ball, whereas a sphere just refers to the boundary of that, the set of all points at distance exactly r. So we are really doing ball packings here, not sphere packings, but the terminology has been established for too long, just like people who are here are learning about elliptic curves. Well, they have very little to do with ellipses, and the terminology is confusing, and almost every single non-mathematical journalist who writes about them wants to write about elliptical curves, and ideally has to be told that no, that wouldn't be correct. I'm sorry, by the way, Zyron, Wikipedia tells me I have to acknowledge the owner of the photo, so he's the one who contributed. He, she, it, I don't know. It looks like a Hebrew name that's male. Anyway, okay, so a 2-dimensional ball, which is what we're calling a sphere in this game, which we're packing, is a circle. A 1-dimensional ball is just an interval. Packing 1-dimensional intervals in 1-dimensional space is easy. You just lay them end to end. They pack perfectly. 3-dimensional balls look like balls. That's why we have the name. So you can imagine asking for, packing packing ping pong balls into a large crate, or traditionally packing cannonballs, or ever since we discovered atoms, how are atoms of a metal, let's say, packed into the crystal of a solid metal? These are all solutions of a 3-dimensional sphere packing problem. And mathematicians have realized a long time ago that even though it's harder to visualize 4 dimensions and higher, the question makes perfect sense. And we can ask the question each dimension. What's the densest? So the general sphere packing question is pick some dimension, which we're going to call little n, and pick some radius, which won't matter because you can scale things, and ask how densely can you pack balls of that dimension and that radius in n-dimensional space, in some huge region in n-dimensional space, so that no 2 of them overlap. Or equivalently, by essentially the same argument as before, so that no 2 of the centers come closer than twice the radius, otherwise known as the diameter. So I will tell you very specific things about this question and some techniques that we know about it and partial answers, but some reasons why it's a good mathematical question, which apply much more generally than just for this particular one. Some of them you can tell from the problem, some of them you can only, realize after a certain amount of, thinking about the problem, recognizing that it shows up in other contexts, etc. So first of all, it's a natural question. It's made up of very simple ingredients of geometry. You can, in principle, explain it to a kth grader for a very small value of k. Maybe I should say to an epsilon, given the name of the of this fund. And okay, so it's a problem in pure mathematics, but it's made of such simple ingredients that it might be expected to show up in various places, both in theoretical mathematics and in various applications, including applications much older than social distancing circles and parks. So that's this item here. There are many generalizations and variations that are suggested. You can, I've already suggested our dimensions. You could imagine changing the geometry, maybe doing it in spherical or hyperbolic geometry. You can imagine packing different objects, right? I mean, instead of metals, which are basically, lots of the same atoms squashed together, you can imagine molecules which have some strange sizes. You can imagine having to pack larger macroscopic objects that are not necessarily sphere-shaped. If they're cube-shaped, the problem is easy, but there are things that aren't cubes and aren't spheres either. The sphere question, though, is particularly nice because of symmetry, as opposed to, let's say, packing pentagons or packing Pac-Man shapes. Because, I mean, the sphere, you already see in 2 dimensions, it has not just reflection symmetry, like each one of these other figures, it has a whole continuous rotation symmetry. So that means the question remains the same if you rotate the plane. Now, you might say, well, if you allow me to take my pentagons and rotate them around, then I preserve that symmetry. Well, that's true, but then you're asking a more complicated question because remember, for a circle, to tell me where the circle is, once you've given the radius, you just have to tell me where the center is. Whereas for this one, if you aren't allowing me to just shift the pentagon around, if you're also allowing me to rotate it, then you also need to specify not just the point, but also an orientation. That's one additional parameter in 2 dimensions, but when you go to n dimensions, the number of parameters of just shifting is n, the number of possible rotations grows quadratically in it, almost n squared over 2. So the circle is the only, and the sphere have the largest possible symmetries for, a bounded object that has positive volume. Solutions to symmetrical questions often have symmetrical answers. They can't retain all of the symmetry. Well, usually they can't retain all of the symmetry, but they can retain a lot of it. The example we saw here, I mean, certainly most of the symmetries of the plane are not going to respect this picture, but it remains the same if you translate by any lattice vector. And even if you fix the lattice vector, you can rotate by 60 degrees and you can reflect. So it has the full symmetries of the hexagon together with all of these translation symmetries. So there is a warning sign here because quite a few of the best sphere packings we know do retain an interesting part of the symmetries of the surrounding space, but sometimes that can lead you astray. There are cases, unfortunately, which aren't so nice mathematically, and even cases where there is an obvious symmetrical solution that is unfortunately not quite right. So we'll see one or two such examples just to keep us honest. And finally, and this is something you can't learn, you have to learn by trying to solve the problem or being in a community of mathematicians and mathematical scientists who have tried to solve it over the years. It's a hard problem, but it rewards various new ideas, which again has to do with the fact that it has simple enough ingredients that it connects to various different parts of mathematics. You will see ideas coming in from, everything from representation theory to, well, we won't actually see Fourier analysis, but that ends up being part of it also, group theory, etc. And it, because it has a lot of variations, you can try these different variations. Sometimes an idea that easily works for one of them will suggest a new approach for another one. And those tools and techniques that you develop for this problem will often have uses elsewhere as well. Okay, so let's see. So one obvious problem you might think of is, well, okay, I don't know how many circles I can, how densely I can pack circles in infinite space. And it's actually a bit tricky to ask the question because, I mean, clearly the number of circles you can fit in R2 is infinite, R2 being just a plane, two-dimensional real space. You need a measure of like density. So what you can imagine doing is take a large circle, ask how many unit circles you can fit into it, measure the amount of space that that these circles occupy. That is some function of the radius, and then let the radius go to infinity and take the limit. Okay. Well, I looked up on Wikipedia, and this question has been looked at, of course. It's still a natural enough question. And you can ask, given the radius of the big circle, how many unit circles can fit into it, but equivalently, given some number of unit circles, what's the smallest radius that will accommodate them? And here are the pictures for the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. When there are two pictures, there is more than one possible configuration. Here, you don't have to have pentagonal symmetry. You can slide the outer circles any way you want. And you already see here, you might not be able to read it unless your eyesight is still way better than mine. But the first few are deemed to be trivially optimal. Then you have something that was proved by Graham in 68, Pearl in 69. This one was proved optimal only in 94. These are hard problems already if you have like relatively tiny circles. Remember, I want to let R go to infinity. And you keep going. Wikipedia goes up to 20 for this question. Oh, there's a few more possibilities for 11. There's a huge set of possibilities for 18. And that's because there's a very tight configuration for 19 circles, which you get from this neat picture of taking a regular 12-gon, which amazingly enough is tiled by 6 triangles, 6 squares, and a hexagon of the same size. So put circles at the centers of each one of them and at the center of the hexagon. And that gives you this tiling. And it turns out you can't do any better with 18 than with 19, just like we saw earlier with 6 and 7. So this one was proved optimal only in 99. This is conjectured to be optimal, but it's still an open problem already for 18. And it's actually not even the first one to be open. In some sense, it's a finite problem because finitely many circles, and it's an infinite region, but it's specified by finitely many conditions. But the problem grows exponentially hard. But assuming that all of these conjectures are correct, because lots of people have looked at these problems, and maybe even if they're not correct, they're not too far from being right. Here's a graph of the answer for the question I asked to motivate this. Here's the radius of the circle going from 1 up to 5, a bit more than 5. And here's the density of the largest number of circles that will fit into it. And so you can see it starts at 1 because the circle of radius 1 will accommodate 1 circle. Then you have to go all the way out to radius 2 to accommodate even 1 more circle. And that means density is going to drop down to a quarter, 1 over 2 squared, then doubled, but it's still only up to a half. And then it comes back up. It comes a bit further up. It comes a bit further up again at 5. And it might not seem obvious that this even is going to converge. And in fact, it does turn out to converge. And in 2 dimensions, we know the answer, but the limit is somewhere up here. It's just over 0.9. So none of the radii reaches it until you get quite high up. And we know the exact number. It's pi over root 12, which is, as I mentioned already, attained by the circle, but by the hexagonal packing. And basically, the reason is there's too much space around the perimeter, and the perimeter is tiny for large circles, but it's a significant part for a circle of radius 5. So, okay, so there's actually a theorem that says, not just for circles, for any, finite, for any tiling problem of a reasonable looking, so basically a bounded region of positive volume, in any dimension, there is a limit. Because I see that I'm not going to be able to get to the end of what I have notes for, I'm not going to outline the proof for you, but depending on how far I'll get today, I might either leave it as an exercise or do it at the end. But that limit does exist, and one does have to actually prove it. And it's not obvious if you just think about circles. I mean, expanding circles. Okay, so that's what happens already in 2 dimensions. Here is something we know a bit more about, which is what do these limits look like in higher dimension? Now, I don't know how, so we have quote unquote epsilons here. I don't know how large epsilon is. So just a very quick review of n-dimensional space, by which I mean, sorry. So in general, space is in mathematics is a set together with some structure, and the structure that's relevant to us is that, well, it's a vector space. I'm not going to bother telling you what that is in general, because all you need to know is it consists of all the n tuples of real numbers. So like n equals 1 is just the real axis. N equals 2, I guess it's called the Argand diagram or Cartesian plane. That's 2-dimensional space. X1 and X2 are the usual X and Y coordinates. 3-dimensional space X, Y, Z. By writing it, by saying it's a vector space, you're allowed to add points point-wise. I mean, coordinate-wise, you're allowed to multiply them by a constant. And it also comes with a distance function. So we sometimes call it a Euclidean vector space, even though Euclid surely didn't think about this past dimension n equals 3. But we regard it as a natural generalization that basically says I want to do geometry. So I would need to know how close points are to each other. And it's given by this formula, which is not as scary as it might look. It just says if you give me 2 vectors, X and Y, I will try to always have vectors with little arrow symbols about them, and the corresponding non-arrow variables are going to be the coordinates. So take each of the coordinates of X, X1 up to Xn, take the corresponding coordinate of Y, take the difference between them, that also forms the vector X minus Y, and then take the sum of the squares and take the square root. So like in dimension 1, you're taking a square of a single thing and a square root, so that's just the absolute value. That's the distance from X to Y. In dimension 2, it's the familiar law of Pythagoras, or the Pythagorean theorem, because we don't know if Pythagoras actually did it. But it basically says the distance from X to Y is equal to the hypotenuse of this triangle. In 3 dimensions, the geometric explanation is, well, you first of all form one of these triangles in the x1, x2 plane. And then any vector, any line in the x1, x2 plane is going to be perpendicular to a line going in the x3 direction. So once you've figured out the length of this, you take this squared plus this squared, take the square root of that to get that, and that is just going to be this formula. And having gone this far, it's natural to define geometry in 4, 5, and so forth dimensions with the same formula and check that it satisfies many of the same properties that we like. There's one other thing I need to define, which might conceivably be new to some more of you, which is what's a unit vector? A unit vector is what I'm going to call any vector whose length is 1, whose distance from the origin is 1. The origin is a vector I'm going to call 0 with an arrow on it to indicate that each one of these coordinates is 0. So the distance from x to 0, you just set all of these y's to 0. It's just the square root of the sum of the squares, but I'm saying it's equal to 1. So the only number whose square root is 1 is 1. So it's basically all the numbers, the sum of whose coordinates is 1. They form a sphere. In one dimension, just 2 points, 1 and minus 1, excuse me, 1 and minus 1. In 2 dimensions, it's a circle. 3 dimensions, it's a ball. Higher dimension, excuse me, it's a sphere. Higher dimensions, it's a higher dimensional sphere. Okay, so now that you know what the distance is, how densely can we pack equal radius spheres in dimension n? Well, so here are all of the answers that we know. Dimension 1 is more or less trivial because, again, lay points end to end. Dimension 2 is the honeycomb packing. It has density pi over root 12, a bit over 90%. This was almost proved by 2 in 1890. There are some questions about some steps in it, but Thurney Fesch thought gave a complete proof in 1942. And that's where the problem basically stood, when I was your age, for most people here. There are many conjectures. There's a famous quote, which unfortunately I forgot to look up the author of, that every physicist, most mathematicians think, and every physicist know, that in 3 dimensions, the packing that you get by basically repeating this procedure that we got, well, okay, it's packing called any one of these is the densest possible. What is that packing? Well, go back here to my triangular packing. Where was I here? Triangles or hexagons. And remember, I got it by starting from the 1-dimensional packing and taking parallel layers of it, each one of which fits in the deepest hole in the previous one. So now I have a 2-dimensional packing, take another layer over it, slide it as far down as it will go. So that means you have to slide it down into one of these collections of holes, either this one or there's another one that will do just as well. And then take the next layer and slide it down, and take the next layer and slide it down. At each point, you have 2 different choices, and therefore you have infinitely many choices for a packing, and all of them occur in nature. Well, not all of them, but a surprisingly large number of them occur in nature. The element cerium at room temperature, for some reason, likes to go A, B, A, C, A, B, A, C. Most elements are either ABC, ABC, or AB, 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 which gives you FCC and HCP in some order. And one of the reasons that this problem is so hard to prove is that, unlike the case of 2 dimensions and 31 dimension, there are these infinitely many possible configurations. So if you want to prove that you have some bound, which, you want to prove some inequality, whenever you prove an inequality, you usually have a sense of what are the case of equality. And here, the case of equality are quite complicated. So that's going to make the proof harder. This was finally accomplished by Tom Hales in 1998. It was a rather complicated proof. It required considerable computer assistance to the point that he was not entirely satisfied with it, even though it was published. And eventually, he actually wrote a whole system of computer verifying proofs just so that he would be able to have a computer verified proof of his theorem, which finally happened 16 years later, he and various collaborators. Okay, so that's dimension 3. Dimension 4, every 4-dimensional physicist knows, and most mathematicians believe that the answer is what you get by taking the same thing and going 1 dimension higher. So the following is not obvious, but it is also an equivalent description. So take my square arrangement here. Where is it? Take my square arrangement here. You could imagine sliding balls into its deepest holes, and amazingly enough, that gives rise to the same packing that we got, one of the same packings that we got starting from triangles. But now go up to 3 dimensions and play the same game, or perhaps even easier to see, take this arrangement in 4 dimensions, and then the deepest holes are so deep that you can fit another copy of that hypercube lattice inside itself and not make the distances any smaller. The reason is, if the distances between vectors are 2, if you go halfway between, that's a vector 1, 1, 1, 1, and 4 dimensions is enough that the sum of those 4 squares is 4. So you take all vectors whose coordinates are all even numbers, and all 4-dimensional vectors whose coordinates are all odd numbers. That gives you what is surely the best packing of 4-dimensional spheres, and it has some extra symmetries that are not obvious from my description. Nobody can prove it. We have guesses, some more secure in 5, 6, 7, etc. dimensions, but there's only 2 more dimensions in which the answer is known, and that's relatively recent. The 8-dimensional case was obtained by Wiazowska in 2016. A week later, Wiazowska, together with the same Henry Cohn, who I mentioned earlier, the 2014 speaker, Abhinav Kumar, who was also my graduate student, not at the time, somewhat later, Danilo Vratchenko, and Steve Miller from Rutgers, together with Wiazowska, figure out how to extend this to, how to adapt this method to 24 dimensions. In both of these, the best packings had been known for a while. And the other thing that happened since I was first invited to give this talk 2 years ago, and that was just a couple of days earlier this week, is that Wiazowska won the Fields Medal for work that includes this result. So this is hard mathematics. I'm not going to even attempt to give you a proof of how either of these work, but I will show you some of the ingredients that inspire this work. And beyond dimension 24, we have some ideas, but we have no hope of being able to prove anything at the moment. And I mentioned already some of the numbers. So 2 dimensions, density is 90%. 3 dimensions, it's just under 3/4. 8 dimensions, it's down to 1/4. 24 dimensions, as amazing as this lattice is, its density is pi squared, pi to the 12th over 12 factorial. And this is not 0.193, it's 0.193%. So as amazing as this packing is, it doesn't even reach a density of 1 over 500. Spheres just don't like to get packed close together in any dimension. I mean, in a large dimension. And for really large n, which was the main topic of Henry Cohn's talk here some years ago, almost all that we know is the best packing is at least 1 over 2 to the n, and at most 1 over 2 to some smaller constant than 1 times n. The best constant we know is almost 0.6. It was obtained by Kabatiansky and Levenstein back in 1978, and it's the best that we have known since, and essentially has not been improved. This goes back all the way to the 19th century, and it's been improved very slightly in that instead of 1 here, we have some small power of n. But essentially as much as was known in the 19th century. And we will show we'll show this, and if I have time, at the end, I'll show you how to get the other one to within, excuse me, not the other one, not Levenstein, but the same thing, but with a factor of with an exponent of 0.5 instead of 0.6. So there's still an exponential gap between the upper and the lower bound. And that's typical of these hard problems. When you can't get the exact answer, you find the best upper bound you can by proving theorems and the best lower bound by making constructions. And in this case, our state of ignorance is such that the best construction that we know is hardly better than the following. Just drop spheres onto your space completely at random, subject only to the condition that no two of them should overlap. And you keep doing that, in some large box, so eventually stop. And you keep doing that, and you stop when there's no more room left. So I've done that here with 10 quarters. I'm not trying to pack them at all close together. This is being done randomly. And let's see, how well am I doing? Is there any space left to go? Well, okay, so here's a way to tell if you have any space left. Remember, these are the centers of these balls need to be at least 2 apart. And if I have any other point somewhere here where I could stick a new one, it would have to be 2 apart, at least 2 units away from each one of these circles. That means if I take those circles and expand each one of them by a factor of 2, do I have the wrong picture here? Yes, I'm sorry. If I take each one of these circles and expand them by a factor of 2, you can see the light circles here, which is where I put my quarters. That's how I knew where to put them to match the pictures. Expand them each by a factor of 2, they should cover the entire space. So that each point in space is covered by one of the circles. Otherwise, I could stick something new here. In fact, here you can see the circles don't quite cover all of this region of space. There's a region here, and there's a region here. So that means I can stick another quarter here and another quarter here. And then I'm really done, at least in this small region, because now the circles cover completely. Okay, if I have circles, or more generally balls of radius 2 that cover space completely, their total density has to be at least 1. And there's going to be more than 1, because this space is going to count 3 times, this will count twice, but each space is counted at least once. That means before I blew them up by a factor of 2, they have to have covered at least a volume of 1 over 2 to the n. So just do things completely randomly, throw spheres blindly into space and there is no room left, and you'll always get within you'll always get a volume, a fraction, at least 1 over 2 to the n left. Of course, you can't be completely blind. You have to be able to tell if there's any room. But you don't have to be at all intelligent or crafty in figuring out where to throw, and do it anywhere you want. It's 1 over 2 to the n. And the embarrassing thing is we don't know how to do better, except by a tiny factor compared to our gap of knowledge. Okay, what time? I know what time it is. How much time do I have left, Benny? 5 minutes?
5 o'clock.
Oh, until 5 o'clock. Okay, that's better, or only by a factor of 2. Okay, what's that? Yeah, so let me at least, having promised you spherical codes, let me at least tell you what they are. And they're basically social distance circles, but on the surface of a sphere. So exactly the same problem, space points on the surface, such that no two are closer than some distance apart, or equivalently surround them by spherical circles, which are half the allowed distance, and require those spherical circles not overlap. This is not a great picture because this point, okay, whatever the actual circle looks like. Or equivalently, such that the corresponding unit vectors don't have too small of an angle between them. Okay, why would we ask such a question? Well, it satisfies some of the same characteristics I mentioned before of a good math problem. Namely, it's made of natural ingredients. You can, once you accept the notion of n-dimensional space, you can ask the question immediately. If you don't know about n-dimensional space, you could certainly ask your epsilon-year-old, how many points can I put on this ball so that no two of them are closer than a quarter's diameter apart. Why would so it also comes with all of the same kind of symmetries. So I wasn't very precise about this before, but two-dimensional space, if you're familiar with, is so symmetric that any pair of points can be taken to any other pair of points by symmetry, provided only their distance is the same. So not only are all points equivalent, all pairs of points are equivalent, provided they have the same distance. And that's also true in three-dimensional, four-dimensional, etc. space. That's also true in a sphere in any dimension. You tell me any 2 points on the sphere and any other 2 points at the same distance, there's always going to be a rotation, the symmetry of the sphere that sends one of them to the other. It's close enough to the sphere packing problem that many of the same ideas apply, but depending on your frame or on your point of view, it's not quite as difficult. So you can get farther with this problem. Some of the ideas that work in parts of this problem might also work for sphere packing. Like the sphere packing question, it is a model for some real-world problems. I mentioned already the methane molecule, which is one of several of the forms CX4, also carbon tetra, fluoride, iodide, etc. They all have this situation where you have a central atom, you have 4 things that are linked to it, and they don't want to come very close to each other. In particular, if you're looking at, we have actually a periodic table there. So look at the column just to the left of the purple, right? So the top one you see there is, how do they do this? They have high, don't look at helium, look at the column to the left. So the blue column, fluorine, chlorine, and so forth. If you go all the way down to iodine, never mind astatine, because you're never going to get enough of it, organostone even more so. But they get larger and larger, and the carbon atom isn't getting any bigger. So it gets harder and harder to fit 4 of them around the central one without 2 of them overlapping. And they don't want to overlap. There is some fractional charge, so they want to stay as far away from each other as possible. And basically, they're moving around on the sphere where they are bonded to the central carbon atom. So subject to that, you want to keep them as far away from each other as possible. And of course, there are going to be atoms which have more than 4 molecules, which have more than 4 atoms around a central one. Also, for that matter, the question that we started with, everybody here knows the Earth isn't R2. It's not really a sphere either, but it's way closer to being a sphere. So any of our problems on, how many of these circles can you fit, that's basically sphere packing on the surface of a 3-dimensional sphere. And in fact, one way to get at the sphere packing problem in n dimensions is to imagine that you're on the surface of a sphere in n+1 dimensions, and then take smaller and smaller balls. So it turns out you can do better than that. And a special case of this question is the question of, which is sort of a local sphere packing question. So you start with a central sphere, and then you have just how many can you fit around this one without 2 of them overlapping. So when 2 of them overlap, they make an equilateral triangle, and therefore the angle between 2 of these vectors is 60. So you have to require the angle to be at least 60 degrees. Okay, so I don't think I'm going to have time to actually prove to you the 2 to the n over 2n bound, but at least I can prove something. And I need to recall one additional bit of n-dimensional geometry, which is what's variously known as the scalar inner or dot product of 2 vectors, which is just given by the sum of products of corresponding coordinates. It has various properties. It's bilinear. Even more obviously, it's symmetrical. X, y, dot y is y dot x. it's more symmetric, is what I was trying to say. The key factor is it's geometric. That is to say, if you take two vectors and you form their inner product and you do a rotation that keeps the origin the same, the dot product stays the same also. I'm not going to prove that here, but a hint is you can write the inner product in terms of the norms, the length squares of the vector x, y, and x plus y. And that gives you, so if it's geometric, I should be able to describe it in terms of the geometry of a configuration of two vectors. So what do I have? I have the length of x, the length of y, and also the angle between them. And it's just the product of the two lengths and the cosine of the angle. And if you believe me it's geometric, then I can actually prove this. Just rotate x or choose a coordinate system so that x is entirely in the first direction, wherever you want that first direction to point. And then if you look at the first coordinate times the first coordinate of y, all of the others you don't have to worry about because they have first coordinate 0 in x. And so you just need to know what's the component of y in this direction. And by basic trigonometry, that's equal to the length of y times the cosine of this angle formed by x and y. So that's why the dot, and that's how you can remember what a dot product is in terms of length and cosines if you forget the formula. So now, in our context, x and y are unit vectors. So x and y, these norms are always 1. And remember, the cosine is a decreasing function. The farther vectors are apart from each other, the larger theta, and the smaller the dot product. Can range from 1 if they're aligned to -1 if they're anti-aligned. So we want to find vectors, as many as we can, in n-dimensional space, capital N of them, such that any one of them is inner product 1 with itself. The inner product of any two of them is at most the cosine of like the minimal separation angle allowed. So how best can you do this for n equals 2, 3, or 4? When for n equals 2, you just have them point in opposite directions. For n equals 3, you can't have them point in up. You can't have any pair of them point in opposite directions. So you might guess, okay, the best I can do is have 3 of them point 120 degrees away from each other. And maybe that will already suggest to you for 4 of them, they span some 3-dimensional space, and they're going to form a regular simplex, which in 4 dimensions is just a regular tetrahedron. It's a bit hard to give coordinates for a regular tetrahedron that makes the first coordinate, the first vector 1, 0, 0. So here's a trick: stick it in a cube. Take every other vertex of the cube. So like 1, 1, 1 divided by square root 3 to make the norm equal to 1. 1, -1, -1, and then change the other coordinates to -1. So here is a graph, plus, 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 and then plus down here and zeros otherwise. And then all of the inner products except x by itself are -1/3. Okay, so I'm going to prove to you that you cannot do any better than that for any number of vectors and in any dimension. You cannot do better than having all of the inner products be less than -1 over n-1, which is what we say here. This is -1, -1/2, -1/3. The reason is, look at the sum of all of these vectors. That's itself some vector in n-dimensional space. Therefore, its length is, the square of its length is some non-negative number. It's always positive unless that vector is 0. Okay, now expand this product out, because you can do it because it's bilinear. Okay, so what do you get? You get x1 times x1, that's 1, plus x1 that x2, that's some angles, that's the cosine of some angles, so it has to be somewhat negative. x3, x1, x3 also, and then x2 that x2 is going to be 1. So you're going to get n terms that are 1, and the remaining n squared minus n terms, which shows one of these n and one of the n-1 others, is at most cosine theta. And that, okay, so I'm repeating this formula here. This is what I had up in this part of the page. And you find that this number, n times 1 plus n-1 cosine, is positive. Where n is positive, so it's not negative. Excuse me. So n is positive, so that means cosine theta is at least equal to this. And in the case of equality, all of the angles have to be such that each one of them is cosine theta apart. Okay, unfortunately, I seem to have run out of time before telling you the next step of the Desart's method, which is basically to say, now apply the same thing to, instead of these vectors, apply it to this multiplication table, where let's say I look for n equals 3 at all of the products of pairs of these. So it's a 9-dimensional vector, but that's okay. It turns out to have unit norm. And so the same inequality applies to it, well, to a collection of these vectors, except it's not quite 3 because the sum of the diagonal entries of this multiplication table is 1. So project away from that, apply this trick here of taking the sum of the vectors and saying the inner product of that with itself is non-negative. And at the end of the day, you get some quadratic inequality, which you combine with the linear quadratic in the xi.xj. You see each one of these cosines here was just xi.xj. There's some inequality like that where you take the square of these and subtract 1 over n. That has to multiply to being positive. That turns out to show you, among other things, you cannot have more than twice little n vectors in an n-dimensional space, such that any 2 of them have an angle of 90 degrees or more of them. You can have 2n, excuse me, because you can have positive and negative unit vectors, like this diagram I showed at the beginning, but you cannot have 2n plus 1. Once you have that, you basically average over n-dimensional space, and that gives you the bound of essentially 2 to the minus n over 2. I'm out of time here, but each one of these programs has another month or so to go, so I leave it as an exercise. So thanks again for your patience, and if there are any questions, I can try to answer them.
Yeah, a moment for a small number of questions. Okay. It might work best if, well, we have some maybe from our participants remotely.
Oh, yeah.
Why don't we take one of those perhaps first, since they are not present?
We don't have any yet,
Oh, we don't.
Okay.
at least as far as I can see in the text.
What I can do is take this microphone and bring it to whoever might want to ask their question. That way the remote audience can hear the question as well. So if you have a question, raise your hand. I'll bring the mic to you.
Wait and tap.
Right.
Yeah.
Yes.
Thank you for the wonderful talk. So we don't know too much about the optimal packings for various dimensions, but do we know anything about kind of the symmetries we might expect for packings of higher dimensions?
Do we know anything about the symmetries we might expect? So that's a good question. In dimensions 8 and 24, the best sphere packing do have amazing symmetry groups. In fact, the 24-dimensional symmetry group is almost one of the sporadic simple groups. If you want to read way more about that, there's this amazing volume by Conway and Sloan, which came out more or less when I was starting graduate school. It's known as FLAG. This is not, I'm allowed to say this because they called it that themselves, short for sphere packings, lattices, and groups. And that will tell you, essentially everything that was known with literally, dozens of pages of references about this problem, let's say up to about 30 years ago, which 25 years ago, which was the most recent edition. But the question of a priori, what can you tell about the symmetry group? Ultimately, you can tell what you can about groups acting on n-dimensional space, which is a lot. And in particular, in some cases, groups acting over the rational numbers, which is more. You can get upper bounds on them, but it's and there have been various sphere packings that were found by starting from a group and than finding a configuration of spheres that's symmetric under it. But so far, we haven't hit the jackpot again, like we did for dimensions 8 and 24, and there have not, okay, that's not quite true. There is one beautiful lattice in dimension 72 that was found that way, but we can't expect to prove it to be optimal, but it might very well be. So yes, it's one of many productive ways of trying to study what the answer might be like in high dimensions. Even though we have the answer in dimension 824, one of the mysteries left is that unlike the proof for spherical codes, I didn't mention this, but we've known for some time that the best kissing number configuration in these dimensions are indeed the local ones for the full sphere packings. There we understand what the symmetry has to do with the proof. Here, the proof that Vyazovska et al. Give for dimensions 8 and 24 still seems to hide the symmetry a bit, so we don't fully understand how the symmetry of these wonderful lattices is connected with the fact that we can prove them optimal. Anyway, I'm sorry I don't have a completely satisfactory answer, but that's the way things are with active research.
We have another question in the room here. Do we have any in the chat?
Mhm.
Okay.
Thank you for the amazing lecture again. I'm just wondering, so all we have talked about is really circles with a set size, with a set
Right.
radius. So has there been anything interesting in with circles that are with different radiuses, or like with a certain rules about their radius that gets like, say, exponentially higher or lower, or?
That's a good question. If you don't constrain the radii at all, then believe it or not, or maybe you can believe it because you've thought about it already, you can attain a density of 100%. Because you can start from, you can do the same thing that I was doing before, put circles any way you want, but you might as well put them as close as possible. And now if you don't constrain me to use circles of a given size, fill in the interstices with smaller circles, and fill in the interstices there with smaller circles yet. And this gives rise to a, if you do it like if you use the biggest circles possible at each point, you get what's known as an Apollonian gasket. It goes back to the age of Greek mathematics, Apollonian, I think. And there's lots of questions and theorems about Apollonian gaskets and their radii. If you specify the radius, if you tell me how many, I give you, 50% dimes and 20% quarters and so forth, that's really a hard problem, and we don't know nearly as much about it as we do. But of course, in real life trademark, you do have to worry about, you have a range of oranges to pack into the crate. How do you do it? So it's an optimization problem, but we can't hope to prove theorems.
One more question, perhaps. There's one here and then one there. So in the interest of symmetry in the room, I'll move over here.
Hey, once again, thank you for the great lecture. Just continuing off of the last question, you mentioned it's difficult if you immediately set the radii of multiple different radiuses that you're considering, like if you're trying to work with spheres or quarters. How does the problem work out if you just say, what if we have two different radii? What might the optimal radii be based on that?
Okay, that's a good question. And that actually is something that shows up in, like, you can imagine molecules or alloys made up of two different objects. And so nature in some sense gives us approximate solutions of this, because it's, if you like form, it's not like I did any of these experiments, and I should say that almost nothing of what I told you today is my own work. I'm all, reporting on stuff that I've contributed to some parts of this story, but none that I've told you about here. And I've certainly not done experiments with alloys, but you can imagine, melting a mixture of two metals and then whose atoms have different ratios, and then cooling it down and seeing what configuration they come up with, and then repeating it with different proportions, different pairs of metals, and you get some idea. What usually happens is they fall into one of a few sets of standard crystal structures. Like maybe they're on a cubical lattice, but the big ones fall in the even numbered, the ones with even number of coordinates, a smaller one in the odd sum coordinates, or you know, variations on that idea. But I don't think it's, look, Tom Hales had to do all this work just to solve the case where everything has radius 1. I think it's probably still an interactive problem, except maybe in some magic cases where you know, magic in the sense of magic numbers, not in the sense of not in the sense of supernatural. Like, you know, if you imagine, take the best possible lattice, the best possible sphere packing in 3 dimensions, and then stick spheres in each one of its densest, you know, its what do you call them, in its deepest holes, that you might be able to prove somehow is the best possible, but I don't know. So it's a good question, but it's still at the range that's too hard. Does that answer the question, Morris? Okay, great.
So I think there was perhaps one more hand. Did you still want to ask the question? Okay.
I'm just curious, you earlier mentioned that they improved the lower bound slightly by like a polynomial.
Right.
How bad is it to just do that? I'm just curious, like how messy or clean that was.
It depends. I mean, the first improve. So the question is, I'm sorry, I haven't been repeating any of the questions so far. I hope that everybody here heard what I was answering. The question of how much harder is it to gain the factor of n or square root of n or whatever it is? It depends a lot on the method. This is not. It's not terribly. They're not terribly tricky, but it's, you know, many people have tried to do this, and every once in a while somebody finds a new technique that works. There are lots of things that don't work, and we have still never gotten beyond 2 to the power minus n times some small constant. So yeah, I mean, actually, I mentioned that Henry Cohn gave a talk about similar topics in 2014. He and his collaborators and postdocs, I think, have you know, have had the record for much of this time. So email Henry Cohn and you'll be able to get the current information about this. By the way, I'm sorry, I should have mentioned this earlier. At least the folks in New York weren't being completely stupid, because Domino Park is bounded on one side by the river and on the other side by a highway, and there isn't enough room here for them to actually stick in a new row of circles. So this much at least is, so that was part of my motivation for showing you what happens for packing in small circles. It's packing in small rectangles, but same idea. This might very well be the best that they could have done. Dolores Park in San Francisco, I don't know why they did it that way. It's huge. Okay, sorry.
Okay, well, let's thank our speaker one more time.